All right, thanks for this chance to speak. Before I begin, I need to comment on this diagram. So as will be clear from this talk, I think there's still a lot to learn from the eternal black hole spacetime, even for evaporating black holes. And so this diagram, the bottom half is not Euclidean evolution, but that we need to milk this spacetime dry. Okay. All right. So in my talk here last year, I pointed out this new property of the ADS-CFT dictionary, that it has some kind of fluidity to it, which was first observed when constructing black hole microstates in the SYK model. So let me review that first. So let me review the construction. This is a construction due to Maldacena and Kurkoglu, where they showed that if you start with the eternal black hole in the SYK model, dual to the thermal field double state of two entangled SYKs, so this is LR, the left and right SYK systems, that if you, there exists a class of projectors Pi on the left CFT, which if you act on the state beta, you generate a very nice class of black hole microstates. So these are states purely of the right system, and they look something like this. The spacetime looks a lot like the eternal black hole spacetime, but with an end-of-the-world brane that cuts off the spacetime somewhere in the interior. Now, when I first saw this, I was very confused, because if you consider the eternal black hole spacetime, the duality says that you have something like subregion-subregion duality, where the operators or the regions A and B are reconstructible on the left and right respectively. So you can reconstruct B from R, and you can reconstruct A from L. So you have this notion of complementary recovery. But in this spacetime, something weird is happening. It seems like both, well, we only have one asymptotic boundary, and therefore both B and A must map to R. So it seems that by the action of this projection, the dictionary has changed. It has adapted to the projection, and then it mapped the entire bulk to a single boundary. What I showed in my last paper is that one can understand this from quantum error correction if one assumes that the dictionary in this spacetime is given by quantum error correcting code, that gives enough structure so that after the action of a certain kind of projection or set of projectors, you can indeed find the dictionary of both A and B in R. What you find is that the dictionary for the modes B are unchanged, but this new dictionary which you generate for the modes A, which are now behind the horizon, depends very sensitively on the projector Pi, and therefore depends very sensitively on the black hole microstate. So this gives a kind of gives an example, realizes an example of these constructions, for example, of Papadodimas and Raju, and the Verlindes of state-dependent interiors for black holes. But I should say that there are some differences, and I think it's interesting to compare the two. So I'm calling this property fluidity. And the point of this talk, well, first of all, this fluidity is a new observation of the dictionary of how ADS-CFT works. And it's bound to be useful elsewhere. And the point of this talk is to harness this new feature to make a connection between entanglement wedge reconstruction and the Hayden-Preskill protocol. I would be happy to talk more about this with anybody after the talk. reconstruction for black hole microstates. Okay, so to begin, yes?
So A is not in the entanglement wedge of any region on R.
Correct, but it's in the entanglement wedge of the entire R. Yeah. I guess, okay, maybe I should say one more comment. You can also do this for long wormholes. So you can consider not the thermal field double, but a state with a very long throat and then project on one side, and that produces for you sort of more typical looking black hole microstates. Where again, the entire thing is the entanglement wedge of the entire boundary. Okay. Any other simple questions about this?
Why do you call it fluidity?
Well, the dictionary changed in response to the projector. Oh, it was you who asked the question? Okay. Okay. Okay, so let me now review the Hayden-Preskill protocol. So what did they say? They said, consider an evaporating black hole B that becomes maximally entangled with the early radiation. That's E. So the black hole is now sort of at the page time. And then throw a message into this black hole, M, which falls in and scrambles. Let's say that this message sent in is in some state psi. After this scrambling, the black hole will now emit some late Hawking radiation, some new Hawking modes, and you'll also be left with a slightly smaller black hole. The question is, how much late radiation do you need such that in addition to the early radiation, you can apply a decoding unitary from which you can extract the state psi with some junk. And they found that the only condition for this to work is that the dimension of the late radiation collected is much larger than the dimension of the message, which says that the amount of qubits in the late radiation just needs to be a little bit larger than the number of qubits in the message. Okay. Now in this diagram, the only important feature is this scrambling unitary. And therefore, you expect the same thing to hold for any sort of scrambling systems, in particular for holographic CFTs. Consider, for example, two entangled CFTs, left and right. This is this discussion is not restricted to SYK. This is general. What this says is that if I throw in a message into R, then allow it to scramble in the system, and then I extract some energy from R, some Hawking radiation, I can extract some Hawking radiation, or just whatever qubits, and then I take that and I throw it into L. Somehow, I should be able to reconstruct this message from L. Okay? You should think of this as sort of as an analogy for a black hole that's evaporating into the early radiation. R is like the black hole, and L is like the early radiation. Okay? Any questions about the setup? Okay. Now, I have to mention that what I'm going to say is somewhat speculative, but I guess this is home turf, so it's fine. But I'll try to state my assumptions. The first one, really important one, is that this is not a purely bulk argument. This relies heavily on boundary unitarity. Okay, but nevertheless, I think there's still something to learn from this. Okay. Okay, we don't need this guy anymore. It turns out to be instructive to start by addressing the monogamy of entanglement argument for firewalls. So you'll see the connection soon. So let's start with a CFT R, which is in the thermal state. So rho R is e to the minus beta HR. The dual spacetime is going to look like a black hole, something like that. And if we compute the entanglement entropy of R, we'll get the area of the horizon H1, this guy over here, H1, plus the entanglement entropy of the modes B, which are outside the horizon. So naively, one can run the amps argument and say, oh, this means there's a firewall. Why? Because this formula tells us that B needs to be entangled with whatever R is entangled with. And so therefore, by monogamy, it cannot be entangled with anything behind the horizon. But then Lenny and Juan would say, no, no, no. You should take into account that there could be another CFT, where so R can be entangled with L. And there's no contradiction with B being entangled both with L and the mode behind the horizon A, because A is part of L. Okay? So this is the famous ER equals EPR resolution of the firewall. Okay. Now the thing that we want to do is we want to extract some energy from R and throw it into L. Or said differently, we want to evaporate R into L. How do we do that? Well, if you turn on any sort of simple coupling between R and L, nothing's going to happen really. They're sort of in thermal equilibrium. But something that you can do is you can introduce an auxiliary system, X, which you should think of as a very large system with many degrees of freedom, but which is in the vacuum, and then turn on a coupling between R and X, delta HRX, which would now allow energy to flow from R to X. So when positive energy goes from R to X, I should say that the next few words I learned from Juan, who's not here. Huh. Okay. I didn't learn it from Juan. No. Okay. Yeah.
Juan's not here. Can I ask if you really consider this to be a resolution? Yes, can you tell me how it works for any other quantum state?
Then let me say no. Okay.
And a technical question, why aren't you coupling R directly to L? I missed that.
Oh, because they're both at the same temperature. So energy is not automatically going to flow from R to L. It's going to go both ways. Okay, so we want to couple R to X. So when positive energy goes from R to X, what happens in the bulk is that you have a negative energy flux, which falls into the black hole. So here you have T UU less than 0. Okay, this is a bit of a side comment. This is problematic. Why? Because you risk violating the ANAC. So this thing, so you know that in the eternal black hole, this thing is equal to 0. And so if you just throw in some negative stress tensor into the bulk, this thing is going to be less into the black hole. This is going to be less than 0. I should say that the integral here, I'm imagining it on the horizon. But it turns out that, and you can prove this, by merely turning on this interaction, you necessarily, there's no way around it, you would insert some positive energy first. It's some small sort of positive energy, transient positive energy at the beginning. You might still worry and say, well, this is a small amount of positive energy, but after it I have a lot of negative energy, so I might still violate this. But that turns out not to happen. And the thing that you have in mind when you say that is that you're secretly thinking about the following integral: TUU u du. This thing computes the energy, the total energy flux that falls into the black hole, and there's no contradiction with this being less than 0, but this thing being being greater than 0. And if you compare the two, the reason why this thing can be positive is because it weights the energy that falls in differently. It gives the energy at the beginning much more weight than the following energy that falls in. So this actually gives a nice constraint on the dynamics of the CFD. You can relate this bound to a bound on the energy, the bound on sort of energy transfer in the CFD. So this implies some bound on energy transfer, and it goes so also the other way. I should say this is current work in progress with Brian Swingle. And I think just preliminary results seems to say that the bound that we get on the boundary is stronger than the bound implied by this. Is that right? Yeah. Okay. Yeah, so I think that's an interesting side comment. Okay. So now let's ask what happens when we, now back to the main story, what happens when we turn on this interaction for some time, allow some energy to go from R to X? What does the space-time look like? I claim that the space-time will look something like this. So now this is the case where delta HRX is not equal to 0 for some time. You'll find, so nothing's going to happen to L. So here's L. But on this side of the space-time, what you find is that the singularity actually moves down. That's R. This is easiest to see from the dynamics of the Schwarzian. So if you think about the 1+1 dimensional version, you find, so let me review that very briefly. Here's the eternal black hole in JT gravity. You have two boundary particles. One for the left and one for the right. If you insert negative energy, then that corresponds to a kick of this boundary particle into the bulk. If you add negative energy, positive energy, then that's a kick towards the boundary. Let's think about just a negative energy for a second. If you do that, then the boundary trajectory is kicked upwards like that, and then you can send a signal from left to right. This is a manifestation of the violation of the ANAC. But what I'm saying here is that first there's positive energy, which means that the boundary particle is going to be kicked towards the boundary first, and then the negative energy is going to try to move it the other way. But in sort of similar fashion, how the ANAC is satisfied, it doesn't kick it too far back, and it hits the boundary sort of short from when it did initially. And then you have this new horizon. So this picture is literally that picture. Okay. The next thing you can do, the next thing to do is to, well, here we started with a thermal field double at some time in the past. We evolved towards the future, and we turned on the coupling for some time, and then we turned it off. Now imagine evolving backwards in time with the decoupled Hamiltonian. So we turn off delta H Rx. Okay? The resulting space-time will look more symmetric. It'll look something like this. That's left and this is right, which in better coordinates looks something like this. Where this horizon is H1. And this horizon is now we have a new horizon, which I'm going to call H2, which is smaller than H1, which had to be true because we've extracted energy from R. There's less energy in R, and therefore you'll have a smaller horizon. And then we have the system X, which contains some of the energy that we extracted from R. The next step, remember we wanted to evaporate R into L. So far we took energy from R and we threw it into X. But now the thing that we need to do is we need to take X and dump it into L. I claim that one can do this. One can find a unitary that can do this. In particular, you can imagine inserting X into the many sort of lightly populated UV modes in L, for example. And then you'll just have some positive energy falling in.
Sorry, just trivial comment, but you're careful about it. You didn't want to couple the R and L directly because you had this argument about the temperature, right? In fact,
correct.
The temperature and also the size effect. So X must be very large for things to actually leak into X.
Yes.
But then by that argument, they can't leak back into L.
Correct.
So presumably much larger than X.
Yeah, I'm imagining, it's a good question. I'm imagining first the coupling between R and X is some simple coupling. So energy just flows out naturally. But I'm imagining the unitary that acts on XL is not a simple unitary. I'm claiming such a thing exists. But I'm going to assume that such a thing exists, which maintains the semi-classical bulk picture. That's my second assumption. So I'm just going to say semi-classical bulk. Okay? All right. So after you do this, you can, well, actually, any other questions so far? Okay, last step, then okay. So something you can do next is you insert X into L, and then time evolve backwards and forwards using the decoupled Hamiltonian. I claim that the resulting spacetime will look something like this. It's going to be a yet longer wormhole. This is L, and this is R. So nothing happens to R. So this is H2. After you throw an X and you evolve backwards and forwards and backwards with a decoupled Hamiltonian, what happens is that H1 will be pushed inside the black hole, or inside the throat. So that's H1. And you'll have a new horizon here, which I will call H3. And if you sort of follow the sort of energetics, H3 is larger than H1, and H1 is larger than H2. Okay? Good so far? So now we can completely ignore X, because we essentially threw X into L. Okay, now let me make a comment about subregion-subregion duality. in the eternal black hole, before coupling R to X, we have, as I reviewed, we have complementary recovery or subregion duality, which looks like where everything on the right of H1 it belongs to R, and everything to the left belongs to L. By here, the left of the horizon, I mean sort of space-like related to the horizon. Let's assume, naively, this dictionary for this final state here. So let's assume that everything to the right of H1 belongs to R, and everything to the left belongs to L.
Sorry, what do you mean by when you say greater than and less than? Are H3, H1, and H2 external surfaces?
Next step, one sec.
Because I mean, it looks like to me, H2 looks to me like the HRT surface.
Okay, that's the punchline. Okay, so building on what Dan said. So as I said, this was all just naive. The density matrix for R, you expect on general grounds that it's going to be very close to the thermal density matrix with a slightly smaller temperature, or just smaller temperature. Beta tilde is greater than the initial beta that we started with. Yeah, you essentially expect this because the Hamiltonian of the CFT scrambles. Essentially, scrambling systems, if you allow them to evaporate, they always have a page time, assuming you allow them to evaporate slowly. Okay, and so if you compute the entanglement entropy of R, you'll find the area of H2 plus the entanglement entropy of the modes B tilde, where the modes B tilde are modes outside the horizon there. Okay, now I claim that I have a firewall. Why? Because, again, due to this statement, B tilde must be entangled with whatever R is entangled with. And therefore, B tilde needs to be entangled with L. But in order to have a smooth horizon, B tilde needs to be entangled with A tilde. But we just said by this dictionary that A tilde is part of R. Yes, I know. Not everybody is Daniel Harlow, so okay. But as Dan is dying to point out, H1 is no longer the RT surface. The RT surface is H2, given this. So everything to the right of H2 is in R, and everything to the left of H2 is in L. So something very interesting happened. The dictionary somehow adapted to the evaporation process. This fluidity kicked in, and the dictionary changed. Now the RT surface of R and of L is H2, and therefore everything within this entanglement wedge is actually part of L. So A tilde is an operator in L, and therefore you don't have a firewall.
Sorry, comment?
Yes?
You mean therefore the argument that you necessarily have a firewall cannot be made just based on the entanglement? You could ask what state they're in.
Correct. The naive argument that I made doesn't apply. That's all I'm saying.
But do you have any additional arguments for why they should be in the right state?
If you assume that I just had semi-classical bulk evolution throughout, since I started with something that doesn't have a firewall, I will end up with something that doesn't have a firewall. There was nothing here that could have generated a firewall at that point.
Well, you could have said that about one-sided black hole based on collapse too. You believe in semi-classical evolution, don't get parallel.
You're not talking about typical states here, right?
Well, these are highly atypical.
Yeah, so
Yeah.
there's no argument that there has to be a firewall, right, here in this state.
Yeah, that's the difference.
Yeah, but there's also no argument that there's I mean, in the starting point, there are pretty good arguments that there's no firewall.
Yes.
I think you've lost that by the time you move to the last picture.
Well, two things. First is making this assumption. Second, this is different from just forming a black hole from collapse and following the evaporation, because as Dan said, there we have an argument to say that there's a firewall.
So you have to wait for a very long time, and so you don't have semi-classical evolution there. So whatever creates a firewall can't be semi-classical evolution, right? If it's just semi-classical evolution, where's the firewall? Presumably, if you wait for a very
classical evolution argument, because if I applied that to a normal formation and evaporation, I would just say that information is lost.
No, but there we have an argument. Sorry. So there we have a monogamy of entanglement argument that says that there's a firewall.
Yeah.
Here we don't have that argument, because that's all I'm saying. And also,
You're saying a little more. You said you tried to make that argument, but then you found you couldn't.
yeah. Which is the same thing as saying there is no argument.
Yeah, but maybe that's true in the general case too.
Yeah.
People try to make the argument that actually you can't.
How much time do I have? 5 minutes?
You could also say it in a more dramatic voice.
Okay. This talk was not about firewalls. Okay, but now, okay. So now let's say, so I claim that this thing. Sorry, did I? So this is the entanglement wedge of L. Yes. Because H1 was the initial horizon that we started with.
Yeah, but I saw some positive, net positive energy.
No. It's net negative energy, but the ANEC is positive. This thing, which measures the total energy that fell in, is still negative. Did I write that? Yeah. So the expectation value of the energy did indeed go down on the right.
Then your second picture, H2 is already there. Which one is the entanglement surface?
Yeah, H2 is an entangling surface, but I was just trying to be.
But you only couple R with X, so you shouldn't do anything with left side.
Well,
Second picture.
this picture. But I want to throw X into L ultimately.
Before you do that,
Yeah, then you have two RT surfaces. H1 is RT surface for L, and H2 is RT surface for R.
which one is the entanglement surface?
Well, it's not a pure state, right? Because they're entangled with X. So they can have different entanglement entropies. Okay. Good. Okay, so now the punchline. Say you first, before evaporating R into X, you throw a message into R. Sometime sort of sufficiently far in the past so that it scrambles before you extract energy from R. And let's track this message everywhere in these diagrams. In this diagram, it's going to be there. In this diagram, it's going to be there. And this, no, we don't care about that. In this diagram, it's going to be there. And in this diagram, it's going to be there. Oh, snap. The message is inside the entanglement wedge. Oh, come on. You ruined my punchline. Go on.
So you turn, to throw the message in, you turn on some source, right? You presume to turn on some
Yeah.
source. When you did the evolution backwards, you turned off that source. You couple delta Rx, you turn on a source, and then you
Oh, yeah.
you turn off the source for the message as well.
Yeah, exactly.
That's why the message is not at the right boundary. Otherwise, it would have been at the right boundary.
Exactly. Well, no, that's why it's not extracted here. What you're saying is that it reflects and falls back to the singularity. It's like adding a shock wave.
So at this point, it's still in the right boundary. It's only after you do this third diagram. Can you just remind me? This is after you throw X into L, the one.
This one?
Yes.
No, this is before throwing X into L. Throwing X into L is from here to there.
Very good. So when you evolve backwards, it was already behind the horizon.
Exactly. Because we extracted this energy from R. And yeah, so the message is now behind the black hole horizon. And so, actually, there's something else I forgot to say. Ignoring the message for a second, commenting again about this, about preserving the nature of the horizon. This sort of tells you how the ER equals EPR resolution is maintained under time evolution or under evaporation. This fluidity of the dictionary is sort of maintaining the smoothness of the new horizon. Okay, just wanted to make that comment. Yeah. Okay. Yeah. So we see how it's yeah. So that's the punchline. The message is inside the entanglement wedge of L because of this fluidity. I just wanna say two things. The first is that the first is that it's interesting how it's the same mechanism that avoided firewalls that also transfer the information. This fluidity saved us on 2 counts. And my final comment is that somebody might say, oh, maybe what happened is that you extracted the information about the message from by extracting X, as in X has the information about the message. But this can't be right for 2 reasons. Well, it's not right for 2 reasons. One is that that's not what happens in the Hayden-Preskill protocol, as in L does not know anything about the message without also including the early radiation. And second, I'll just give you an example where we know of something like this, where X knows nothing about the message. So consider a slice of global ADS. I thank Brian for pointing this out to me. Consider dividing it into 2 regions, B and A. The RT surface separating these 2 is somewhere there. Consider encoding a message somewhere deep in the bulk in the entanglement wedge of A. Now let's divide A into 3 small subregions, such that none of whose entanglement wedges includes this message. Let's call them A1, A2, and A3. Now notice that B knows nothing about the message, A2 knows nothing about the message, but the combined system, BA2, knows everything about the message. So that's what's happening here. X knew nothing about the message, but when you included it with L, the new entanglement wedge has access to the message. Okay, yeah, that's all I had, actually. Thank you.